our today's lesson, and today I want to focus on redox titration. I'm going to use an example that gets brought in most examinations in as far as the different curricula in our countries in this world are concerned. And what I want to discuss today under redox titration is a titration that gets done between an oxidizing agent, for example potassium manganate 7, and a dibasic acid of this chemical formula. For example, I can say let me pick the oxidation state of this potassium manganate 7 to be 7. So I'll say the manganate 7 ions are possibly going to lose 5 electrons to end up giving us the manganese 2 ions. So in this case, the manganate 7 ions are responsible for the purple color of this oxidizing agent. So the purple color will end up disappearing and the solution turns colorless because the manganese 2 ions, which are colorless, are formed. So in such a case, we don't use an indicator to confirm the end point of the reaction because the oxidizing agents themselves undergo a change in as far as the appearance of what we have in these compounds are concerned. So, and for these oxidizing agents to completely oxidize whatever they want to oxidize, we always advocate that they actually end up being acidified. So they should be acidified for them to completely oxidize any other compound that gets used in as far as redox titration is actually concerned. So assuming I'm actually given this tool and I have to get maybe the value of X at the end of the reaction in relation to this titration, I can assume to have a molarity of 0.0125 molar for the potassium manganate 7. I could probably say let me pick 5 grams and dissolve in 1000 centimeters cubic of this solution. So I've picked 5 grams of this dibasic acid. This is a dibasic acid. Why do I say dibasic? Di means 2, so it has 2 hydrogen atoms, so it's actually a dibasic acid. So the 5 grams have been dissolved in 1000 centimeters cubic of water, or the 5 grams have been dissolved in a liter. That gives us the concentration, the amount of the solute or the solid that gets dissolved in a liter of a solution. Concentration. The number of moles found in a liter, or the number of moles found in 1000 centimeters cubic. So you can say 0.015 or 0.0125 molar or 0.0125 moles per liter. So this capital M symbolizes the number of moles in a liter or 1000 centimeters cubic. I can as well, let me assume the average volume of the oxidizing agent used in as far as the titration is concerned is 31.75 centimeters cubic, and maybe after dissolving 5 grams of this dibasic acid into 1000 centimeters cubic, I only used 25 centimeters cubic. Good. And maybe I can have the reacting ratio to be 2 to 5, or the mole ratio to be 2 to 5. So the first question can be moles of the oxidizing agent that reacted. It is very simple. 0.0125 moles are contained in a liter or in 1000 centimeters cubic. What about this one? Because this is the volume that got used. And if this is the volume that got used, it must be containing the moles that reacted. But now, on average, the concentration of this compound is actually 0.0125. That means in every 1000 centimeters cubic of this solution, there are 0.0125 moles. So in every 1000 centimeters cubic of this potassium manganate 7, there are 0.0125 moles because of this capital M, the molarity. So what about the volume that was used, which must be containing the moles that reacted? Good. So let's see. So we are going to have cross multiplication. So 31.75 multiplied by 0.0125 divided by 1000. So you have 0.000397. 0.00397. So you have 0.000397. Good. Those are the moles that reacted. 0.000397 to 6 decimal places. After I'm done with that part, I can get the moles of these that reacted. The moles of the acid that reacted. The moles of the acid or the dibasic acid that reacted. If we come back here, the mole ratio is 2 to 5. That tells us 2 represents these moles. What will 5 represent? 2 represents these moles. What will 5 represent? Because these are the moles of the potassium -7 that reacted, and the mole ratio is 2 to 5. So 2 for the potassium -7 is equivalent to the moles that reacted. Good. What will this 5 actually represent? That I've written here. So I just cross multiply. So I'll say 0.000397 multiplied by 5 divided by 2. So 0.00099925. So the moles here are 0.00099925. Those are the moles of the acid that reacted. Okay, we can come back here and now get the molarity of this acid, because the molarity of the oxide or the oxidizing agent is given. So we shall come here and say these moles are the ones that reacted, and this is the volume that was used. So that means the moles that reacted must be in the volume that was used. But we are getting the molarity. That means how many moles can be found in 1000 then? So we shall say 0.00099925 are the moles found in the volume that was used, which is 25. Good. So what will 1000 centimeters cubic contain? That gives us now the molarity, the moles in 1000. So we shall come here and we shall say now answer, this one here, we are going to cross multiply. Answer times 1000 divided by 25. Answer times 1000 divided by 25. So it gives us 0.0397. 0.0397. And because they are the moles in 1000, we are going to write capital M. Good. Very good. Okay, then we shall come here and say now the relative formula mass, or the relative molecular mass of a compound, or the molar mass of a compound, can be obtained by taking the mass divided by the moles. Where does this one come from? You can have a simple representation of a triangle where you can have here as the mass, you can have the relative formula mass, and you can have what you call the moles. So how do you get the relative formula mass? Mass over moles. Mass over moles gives you the relative formula mass. This is here. So we shall pick the mass, 5 grams, that was dissolved in a liter, divide by, ensure when you pick that mass and you divide by the molarity, the mass should be in 1000 centimeters cubic or in a liter. So 5 grams per liter over the moles in 1000, 0.0397. So we want to get the relative formula mass. So you can just obviously say the answer, so we shall say 5 divided by 0.0397. So you get 125.9. 125.9. Good. So you can just round off and get 126. Okay, 126. So it will be grams per mole, the relative formula mass of that acid. So that means the relative formula mass of the acid H2X dot 2H2O is actually 126 grams per mole. But we want to get the value of X. We know very well hydrogen has a relative atomic mass of 1, oxygen has a relative atomic mass of 16. So we shall come and say hydrogen 1 times 2, because there are 2. We shall have 2 plus, we don't know X, then plus hydrogen is 2, then 1, so 2 times 1 is 2 times 2 again, that is actually able to give you 4. Or you can just say 2 into hydrogen is 1, 1 times 2, that is 2, then you add to oxygen is 16. Good, is equals to 126. So 2 plus X plus, that is 16 plus 2, 18, 18 times 2, 36, is equals to 126. That will be X plus 36 plus 2 is equals to 126. So X plus 38 is equals to 126. Good. So X is equals to 126 minus 38. Good. So we are going to take 126 minus 38. We are going to get 88. Very good. So the value of X, is equals to 88 grams per mole. Now if you have H2, then X2 molecules of water of crystallization, in chemistry this will obviously be an acid called oxalic acid. An oxalic acid is also referred to as ethanedioic acid. So it's actually either oxalic acid or ethanedioic acid, whose chemical formula is H2C2O4, then 2 molecules of water of crystallization. So that this C2O4 should represent the X, because you have the H, we have the H, we have the H, we have the H, so that means X is represented by C2O4. And then we have the 2H2O, the 2H2O. So that means this is X. So our X is C2O4 and our X is 88. Look at that. So that means this X should give us 88. Let's try and see. Carbon is 12 and oxygen is 16. Carbon is 12, but carbon atoms are 2, so 12 times which is actually 24. One carbon is 12, but there are 2 carbon atoms, so that's 12 times 2, that is 24, plus oxygen is 16, but there are 4, so 16 times 4, that is actually 64. That gives us 88. Good, which is actually here. So oxalic acid or ethanedioic acid. Remember this: if ethanedioic acid is not actually present, in most cases, as far as redox titration is concerned, the leaven also is what we call hexandioic acid. So oxalic acid is also called ethanedioic acid. But if oxalic acid or ethanedioic acid is not present, they can use hexandioic acid in the titration. So H2C2O4 dot 2 molecules of water of crystallization, oxalic acid or ethanedioic acid. If this is actually absent, good. Titrations can also apply the use of hexandioic acid. Hexandioic acid. They are all actually synthetic acids or artificial acids or manufactured acids. But oxalic acid can also be actually found in fruits and vegetables. So oxalic acid or ethanedioic acid, which can get used in this process called redox titration. But as well, we can also use hexandioic acid. So you either use oxalic acid or hexandioic acid. But oxalic acid does not mean the same as hexandioic acid. There are different types of acids. Oxalic also means ethanedioic, but you can also use hexandioic acid in our titration process if oxalic or ethanedioic acid is absent. Great. Thank you so much for your time and have a nice time.